Hi everyone, I am Saransh. I'm an undergrad at the University of Delhi, and right now I'm working as an intern at IRISEP. So for the past few months, I worked on this new backend for vector library, a new SymPy backend, and that's what I'll be presenting quickly today uh, under the supervision of Dr. Jim Piversky. Okay, so quickly introducing vector before moving ahead. Vector is a Python 3.8 plus library, and we also have support for Python 3.6 and 3.7 in older versions for 2D, 3D, and Lorentz vectors, especially arrays of vector. Or um, the thing that people are most interested in are the awkward arrays of vectors to solve common physics problems in a NumPy-like way, to construct, manipulate, and do physics with high energy physics data. Vector can perform numerical computations using its three existing backends and then one another new backend, that's SymPy. So the existing three backends are the pure Python or the object type backend, a NumPy backend, so NumPy arrays of vectors, structured NumPy arrays, and then awkward arrays of vectors. Hence, it is used by experimental physicists in their analysis pipelines for analyzing high energy physics data. Vector also supports other few libraries, and this supports comes through awkward arrays. So, for example, you can pass in, or you can use Dask awkward with vector. You can use awkward's JAX backend with vector for differentiation, and the awkward backend of vector also supports just-in-time compilation using Number. And also, the object backend also supports just-in-time compilation using Number. Okay, our motivation for this particular mini project or adding SymPy as a backend, there were two major motivations. One was that vector and most of the scikit ecosystem is at the moment majorly or primarily meant to be used exclusively by experimental physicists because it operates on numerical data. And then vectors compute functions were written to operate only on data containers initially by Jim when vector was initially written out, which is right now tested uh, in vector CI using Uncompile 6. But Uncompile 6 is will soon be going away when Python 3.8 reaches its end of life. So um, one of the motivation was that we wanted uh, to expand the user base of vector so that theoretical physicists could use vector along with experimental physicists. And the second motivation was that we have this suite that we wanted to maintain and switch from uncompile 6 to something else that could make sure that the compute functions, the existing compute functions, the compute functions that are being added inside vector now keep working only on the data containers and not on the numerical data. So adding a SymPy as a new backend would kill two birds with one stone. Along with experimental physicists using vector for numerical computation, SymPy would allow theoretical physicists to utilize the library for symbolic computations and their work, and it will allow the developers or us to get rid of the uncompiled 6 dependency in vector CI when Python 3.8 reaches its EOL. So the tests written for the SymPy backend will ensure that the compute function keeps on running as they are right now. Okay. Okay. Uh, let's quickly look at a small example for how the SymPy backend works. So you should be able to run this on Binder, uh, or you can clone the repository locally and launch it using JupyterLab. Um, yeah, so I'll be using scikit-test data for a sample data file approved for reading the file, vector and SymPy for the main parts of the doc. So let's start by importing the required libraries and reading the data. And then we can extract the data using the T-tree, using the events key. Just for the sake of showing around the SymPy backend, let's take only two muons, with two data points, the first muon and the first muon, the second and third list as a sample data. And now we can create our object type vectors, something that has existed in vector for a long time. using these data points. So we can pass in the coordinates inside our momentum object 4D classes and perform all the vector compute functions or u functions on it. So for example, we can perform the delta R operation on the two created object type vectors, and it works. SymPy vectors, on the other hand, do not require numerical coordinates. So instead, what we can do is we can create, or what we're supposed to do is we're supposed to create symbols, or more broadly, SymPy expressions. And then we can pass those expressions or symbols directly into the new, the momentum SymPy classes. So these are almost the same as the object classes, but instead of accepting numerical data, they'll accept SymPy symbols, or even like more broadly speaking, any SymPy expression. So let's just specify that we want four symbols for each of the vectors, and we can specify that they're real, or if they're positive, or if they're non-zero, or if they're negative, anything that SymPy would work with. So right now, let's just specify that all of these are real and pass them into momentum SymPy classes for vector, and everything works. So similar to the backends, one can perform all the vector methods, all the vector compute functions, like for example, delta R on SymPy vectors. They work exactly the way they would work on object type vector, with a small caveat that I will discuss later. And all the methods automatically work on SymPy symbols or expressions. So Jupyter will automatically turn on SymPy's LaTeX printing by default, but one can toggle it in terminal using other SymPy functions such as SymPy in its session. So if I run this particular cell, it will automatically run the computation on the symbols that we created and the symbols that we passed into our momentum vector classes for the SymPy backend. Uh, yeah. If you run this in terminal, it would not show it in LaTeX, but you can run SymPy.init session, and after that, it would start showing the output in LaTeX too. So given that all the computation results are SymPy expressions, or either SymPy expressions or SymPy symbols, any SymPy functionality can be used on them. So for example, to check if our result is correct, we can use the SymPy's substitute method and substitute the original values that we took here. So for example, we can uh, obtain these values using muon1 obj.px1 and substitute them, .px, and substitute them in this particular expression that we found, that we obtained. Running this, SymPy would automatically substitute it for us, and then similarly we can substitute the values for the second SymPy vector as well. Yeah, that works, and SymPy does everything for us. Finally, to evaluate the numerical results, so SymPy would not evaluate things like trigonometric functions or natural constants. It would leave them as it is, but one can use SymPy's evalf method to carry out the final computation. So we can call evalf on the final result, and SymPy would output the numerical value, which would match the numerical value obtained by the object backend. Now, there would be a slight difference in the final decimal places, if I'm not wrong. That's because SymPy uses MP math for its floating point arithmetic, and that's where the difference is coming from. But the first few places, I think the majority of the first few places would be the same for the numerical backend of the vector, and when you evaluate a particular SymPy expression produced by vector. And similarly, one can experiment with larger symbolic expression as well. So let's boost a vector and obtain the px coordinate using the object backend. So we can create a momentum type object vector and then just boost it using its beta 3 and obtain the px coordinate. The exact similar operation can be carried out using the SymPy backend. So let's create a SymPy vector. We'll again create 4 coordinate containers or symbols and specify to SymPy that all of them are real, and pass them like we passed a numerical data to momentum object classes. To the momentum object class, we can pass our symbols to the momentum SymPy classes. The operations will now work on SymPy symbols, all of the operation instead of numerical values. So doing v.2 beta 3 will automatically convert the coordinates, transform the coordinates uh, as symbols. So for example, here we don't see LaTeX printing because the result of this particular operation is not a SymPy expression, but it's instead a vector. Um, so if I extract the px coordinate, or if I extract the pt coordinate, for example, that would be printed in LaTeX because that whole thing would be a SymPy expression. Um, I think that should work if I do it here as well. Yeah, that works. Uh, Doing the exact same thing that we did here, extracting the px coordinate, uh, but this time with the SymPy backend, and it works. It gives us a very complicated result, but um, everything is printed in PT LaTeX. Given that the result itself is a SymPy expression, not here. The result here is a vector, but the result here is a SymPy expression. So we can use SymPy's other functions such as simplify to reduce or simplify the result. The simplification step takes some time, but it usually just depends on SymPy. And there are other multiple methods that one can use. For example, one can just rationalize the expression or just simplify the trigonometric uh, values inside the expression. And I think simplify just combines all of those simplification methods and does it in one step. But yeah, you can pretty much call any SymPy method on these expressions obtained through vector. Finally, we can again substitute the values to evaluate the SymPy expression so that we can validate the result if it's working accordingly and if it's matching with the object backend. Yeah, once we substitute the values, SymPy does substitute the values, but it does not evaluate it automatically. And finally, we can call the evalf method to evaluate it. So uh, I think the first, a good amount of first decimal places should match with the object type backend, and the last few might not match. Yeah, okay. That was a small demo of the SymPy backend, but it was, I think, a dummy problem. I haven't uh, actually applied this on a real high energy physics analysis pipeline or something that a theoretical physicist would do. But everything should uh, ideally work, given that all the tests are passing and um, every dummy problem is working right now. Okay. So this is how the SymPy backend works right now, or the vector as a whole works right now. So one can right now pass two types of values, coordinate values into vector classes or vector coordinate classes. So it could either be numerical values, they can be either uh, standalone numerical values or arrays, or numpy arrays or awkward arrays, but with numerical values, or they can be SymPy expressions or SymPy symbols. These can be passed into the coordinate classes, or and these coordinate classes can be passed into the vector classes. Or like we saw, we can directly pass these expressions or values to the vector classes as well. Now, whenever an operation is performed on the SymPy type vector, it goes through a shim layer that maps SymPy functions to NumPy functions. And these map functions are then passed on to the compute functions. And given that the compute functions are duck typed, they don't care if the coming values uh, are just the data containers or the numerical values. They just operate on them on the data containers. And once they operate on it, the final result is wrapped as a scalar vector or an array of vectors. And depending on how it is wrapped, you can either perform SymPy operations on the results, NumPy operations on the results, or awkward operation on the results. Okay, there's one small caveat with the SymPy backend of vector right now. And this is intentional and not a bug. So operation on SymPy vectors are right now only, uh, and I think in the future too, are only 100% compatible with numeric vectors, the Python, NumPy, and Awkward backends if the vectors are positive time-like, that is, if t square is greater than x square plus y square plus z square. The space-like and negative time-like cases have different sign conventions, hence to make SymPy simplification work and to not add if conditions inside the shim layer, these sign conventions are ignored uh, so that only the sign convention of uh, positive time-like vectors is the one that's treated correctly. Okay, that was all about the SymPy backend of Vector, but Vector has also gone through some very major developments in the past 6 months, including I think around 5 or 6 new releases recently. So Vector now supports NumPy 2.0. Vector can now work with Dask awkward, so you can pass in Dask awkward arrays inside vector constructors. There's also JAX support through awkward arrays. There wasn't much done inside Vector to support JAX, but it automatically started working once awkward arrays um, the JAX support in awkward arrays was revived. Coffee is switching to Vector internally, and I think that switch is almost done. It might Coffee might make a new release in July with the new switch where they're internally all their internal vector modules are being dependent on are using vector or scikit vector. There's better subclassing support for awkward mixins. There are less bugs now, and there are also better docs for subclassing vectors. This came from a coffee switch. And there's a uniform and a strict promotion/demotion scheme for geometric coordinates. You might also see some new errors pop up in your scripts if you uh, update your vectors version. But then there are also helper functions such as the like method that would help you quickly migrate from the older versions to the newer versions. There's also momentum support for transformation methods. For example, momentum coordinate support. So for example, two vector star D methods or two coordinate names method now support momentum coordinates as well. And there have been multiple other quality of life fixes and features. Most of them were requested by physicists, or most of them were the bugs were reported by physicists. So most of the development of vector in these past 6 months have been spearheaded by physicists' requests. Finally, Vector had 5 new releases this year: V1.2 all the way to V1.4.1, and the changelog details has details about every release. And you can also check out Vector's GitHub repository, the releases section, to see how Vector has changed with every release. Okay. That would be it. If you're using Vector, you can cite it using the small button available on GitHub. And recently, Vector crossed 1 million download. That I think is very nice. Great. Thank you for your time.
Thank you very much, Saranj. That was very impressive. I love the way that these packages can combine together in such a neat way. So, yeah, let's open up the floor to questions and comments. So just raise your hand if you have something that you'd like to ask.
Yes, I haven't
Yes.
really experimented with writing C code, and I actually haven't even experimented with symbolic differentiation. These are the things that I should look into, given that the SymPy backend is working well now.
Yeah, thanks. I guess that was inspired by Henry's comment in the chat that SymPy can write C code too. Jim.
Yeah, I think that the conversion of coffee to scikit vector is done. I've seen the PR that switches from coffee's internal vectors to SymPy vectors, and I'm sorry, to SciPy, scikit vectors. There we go. And it was extremely straightforward. It was just uncomment the one and comment the other. So if that's, I don't know if that's in a release yet, but it's that should be very smooth coming along.
Thanks, Jim. Any other questions or comments? Eduardo.
Okay. Yeah, a quick one, since you mentioned the coffee. So that's of course a big thing. Did you check any performance of the package to switch? Since you know, well, vectors, of course, you bundle certain number well, 4 numbers essentially together. Did you check any performance, or this is on the menu?
For the coffee upgrade, the coffee switch, I don't think we
Yeah.
checked performance, but I think it was that coffee's scikit-learn vector was built upon coffee's initial vector modules. So it's more mature than the existing coffee's vector modules. And I think it should be better, or at least on par with performance of coffee's vectors.
Okay, yeah, thanks.
Okay, thanks, Saransh. I guess if we had a little bit of time, so I was just I was slightly intrigued by the numerical comparison between going through SymPy and doing the direct calculation in vector. It almost looked like you were getting about sort of a matching on about the float 32 precision. And you mentioned something about the back end being slightly different. I was surprised that it starts to diverge so early in the digit sequence.
Uh, I'm not sure if uh, MP math is used anywhere else, but SymPy does not depend internally on NumPy. It only depends on MP math, and I haven't really looked into why it does that, and how is it actually different than the other numerical libraries available in the Python system.
Yeah, because it didn't look like you had like particularly perverse values or something where you would get some low precision intermediate result. So it was just a curiosity.